Hey, hi, good morning. Good evening,
Hi.
hi, Kalpana. So when is your joining date, Kalpana? Hello? Okay, yeah. So I think everyone joined. Mamta also joined. So let me start sharing my screen.
Good
So,
morning, Shiva.
yeah, good morning, good evening, Mamta. So let's get started. So last week we were discussing with the two pair RDDs, pair RDDs mainly, pair RDDs and their transformations and actions. Okay, I'm keeping you all on mute for a while. Yeah. So the next topic in our syllabus is loading and storing. Same load store commands in your pig. So loading different file formats, especially we'll see. So files from local file system, files from HDFS, and reading a list of files from a directory. So that is one scenario. So LFS, HDFS, directory, reading a pattern match based directory list of files, and sequence files and ORC files. Okay. So we'll discuss these many today, and few popular file formats like Parquet and JSON file formats we'll see at the time of Spark SQL, because you will find bit complex in handling them just for ORC. If you observe, you can read the ORC also. Of course, we'll see ORC, all other CSV files and these things in Spark SQL as well. But here Spark native will limit our scope to these topics. Okay, and after that I'm planning to cover shared variables concept, under which we have broadcast and accumulators. Okay, so anything, so most popular the file formats. The first ones, the few things that you should mandatorily know is the text files and different types in text files like key value or basic text input format, or sometimes, very rarely, sequence files, and most frequently ORC and Parquet, because these two are the most optimized and fastest performing. And out of these two, ORC is the fastest one, right? So for some of the guys who attended the Hadoop training sessions, they got in more in uh, details about these things, like why they should go for ORC or Parquet in real time. Okay, for now, yeah, let me get started with the contents. So Spark can access data through your MapReduce input format and output format interfaces. So almost all the file formats that are supported in the MapReduce, they all will be supported in the Spark as well. Okay, and it also supports the interaction with LFS, local file system, interaction with Cassandra, integration with HBase. All these are possible. Out of which we'll see into Spark's integration with LFS, HDFS, and HBase. HBase also we'll see at the time of Spark streaming. I will show you. I'm not spending separate section on that topic on that. I will show you at the time of Spark streaming examples. Okay, and we can see the text files and JSON files, all these things being processed very easily, and CSV files with the delimiters. Okay, and some of the other file formats like sequence files and any object related files like binary files. Generally, we don't go to these two options, either sequence files or Parquet and ORC. Okay, so just reading from a HDFS, so we might have already, we have been seeing that scenario. So how to read files from just your Hadoop FS minus LS. So if you see, so let me take one file, just our typical file. So just readme.md. Reading from HDFS, we have very simple syntax. So SC on Spark context, we have text to file method available. So which takes by default, if you give the path, relative path of any file, that will be searched in the HDFS file system. Okay, so this is now RES71 is an RDD. It reads this and it printed the first record, hash Apache Spark. Or if you see here, so total 98 lines of code is text is there. So on the other hand, if you have the same file on your local file system, let's say I have this derby.log file. Okay, so if I want to read this, so just copy. Only thing is you need to give the file URI as well. So file : home/cloudera/derby. So just with file : so file URI, it identifies this is a local file system. Okay. On the other hand, if you can also give for the above method, you can give the HDFS URI as well. HDFS : / your host name : port number and followed by your path. Okay. So RES74 dot. So first record. So this is the first record in this. Yes, correct. That's the first record there. Just if you want to see take of 5. So these are the first few 5 records. Okay. Now, coming, so this way, if you use file : URI, so it can read it from your local file system. If you don't use it, by default, it points to your HDFS file system. So reading a simple file, directly giving the file path. So no doubt it's able to read it. Okay. Now, if you want to save this RDD back somewhere, okay, res74 dot save as text file. Save as text file. Yeah, I hope you guys are concentrating, and I might not be. I mean, these are like, it's not a concept to repeat again and again. These are mostly like syntax. Okay.
Yes, Shiva, it is. I got it. Like, so what you told was relational path. It looks for the HDFS. Otherwise, file is local file, right?
Correct. And what I'm requesting you is like, so this is just a more of like a syntax oriented. Please try to catch it in one go. Okay. Instead of I repeating, because it's all just a matter of syntax. You just have to practice that. That's it. There is nothing conceptual oriented that I have to explain here. Okay. So if I want to store it, the same res74 somewhere on the HDFS /user /Cloudera /res74 out. Okay. So it got stored so quickly. See, if you check that -ln /user /Cloudera /res74 underscore out star. Okay, so you might got the same file content there. So this is the file contents of that. In the same way, the local file you loaded into Spark and stored this onto HDFS. And similarly, the HDFS file, if you want to store that onto your local, so you can use the same API. So save as text file. So this time you give it with file URI, local file system URI /home/Cloudera res71 out. It's so fast. res71 out. So you can see the same, the readme.md file from HDFS. I'm able to copy it onto local. Okay. So next, so this way you can read from your LFS and you can write into your LFS, and you can read from HDFS and you can write into HDFS. Next thing, so one of the popular problem in HDFS with the MapReduce, we were struggling a lot to achieve this functionality. So maybe in MapReduce, I didn't cover this for most of you guys because it's a bit complex there. So if you have a directory with small files, all might be of similar schema. Okay, so they might be of like a plain text files or a similar schema, the same schema. But if you keep on receiving very huge number of small files, but maintaining the huge number of small files in Hadoop adds a extra headache on the name nodes metadata management, right? So as I was telling you, so if you have 1 million files, each with 10 MB, so instead of storing those many files, the same 100 GB files, if you have just 1,000, so which is equivalent, which will be efficient way to store in Hadoop. So that small files problem in MapReduce we solve it. I will tell you the steps how we solve that. Let's say if we have 1,000 files in a directory, okay, all with similar type of schema. What we do is we read each file into a sequence file. We read each file's content into sequence file key value format. Sequence file is nothing but a sequence key value format, right? So we read all the 1,000 file names into the keys. So you'll have something like this. So file 001.txt and all its contents, and file 002.txt is the second file name and all its content. So we read the file name into key and all its contents into just one line. Just one line. All its contents of file 1.txt into one line and as a value. And this sequence file now is just one file and can be processed in a MapReduce job. And based on the size of this sequence file, those many number of mappers will get triggered. Otherwise, even though each of these files are like 10 MB or 1 MB sizes, so you will get 1,000 map tasks getting triggered. So that is a burden on your YARN framework as well as your HDFS framework to maintain that much of metadata. Right? So to avoid such scenario, in MapReduce, we were reading all the file names into the keys and file values, file contents into the value part of it. So you'll find 100 records in your sequence file. So those 100 records, keys with file names and contents with values. So that's the concept we were following in MapReduce and traditional Hadoop.
Shiva,
Yes, Kalpana.
here it's a content means details of the file or actual data of the
Actual data. So if I say here, the cat of this,
okay.
okay, everything. So this is how we were solving this problem in MapReduce. Okay. So for that, we had some whole text reader. Maybe if you have a Tom White's Hadoop definitive guide, so you can find this use case there, how to handle small files problems. Or you can find a couple of articles in our blog also, handling small files or merging small files. You can find those if you want to further explore on that. Okay. Somewhere here like sample MapReduce. Okay, I think somewhere I have that. Just we have to search that, that's it. See, merging small files into sequence file. So if you check this article end to end, so you will find the approach that we were following to solve the problem of small files. Okay, now, so instead of doing this much of stuff by us, so Spark has given a very simple method that, so here what I am doing, like I'm reading all the files, entire file contents into one single record and making that. So in this directory, I'm reading all these files into one sequence file. So file names as a keys and values as the contents. In this file, just using the sequence file key extractor, if I extracted keys, these are the keys from the output that I generated. Okay. The same functionality, instead of doing this much of stuff, so if you want to achieve in your Spark, we have one very simple method. So sc dot whole text file. Okay, just sc dot whole text files and give your directory. You can give your directory as a plain directory which includes all the files, or you can give a regular expression pattern as well, /home /cloudera /desktop / let me see what are the files that I have on my desktop. So I have some files like data.txt and abc.txt. Okay. So I have this abc.txt. So if I read this star.txt, what I will get is val a pair RDD. Always pair RDD, pair RDD. So this pair RDD will contain keys as file names and values as file contents. You can refer that. So this is an RDD of string comma string. So if you just want to get the keys, I know that you might have forgot all the methods on the last weekend itself. So to get the keys, dot keys, and that is another RDD. If you want to collect them, see, so these are the files that got loaded: data.txt, abc.txt, and dimensions.txt. And if you want to have a lookup of this, lookup by key. So key is a string. Just provide abc.txt. Let's see what will happen. These are the contents of abc.txt, right? Just now we can see here. So now if you have a pair RDD, if you can in one single shot. So might be some setup issue, Mamta. Try to explore like as much as you can. So
Yeah,
that,
yeah, I'll talk to you later. Probably at the end, I need 5 minutes of your time.
yeah. Okay.
Maven setup.
Maven setup again?
No, because I tried, even after that, it is getting error.
Okay, because it seems like I explained it twice.
No, I did all that.
Especially for you.
I did all that. It is still showing errors because it is not finding those context.
Okay. Did you check our video?
Yeah.
Okay.
Based on that only I did.
Okay, then we can see not a problem. Okay. The thing is, I want to, reduce as much repetition as possible this week and next week because I'm planning to complete. Okay. If I had time, like I would have extended. So that's the thing. Okay. Now, so unpaid RDD, same like here. If you want to get keys, if you want to look up by a file, or if you want to map, or like a map values. So if you want to map values, if you want to get all the values, you can get them. So map values is another RDD, right? So map values is another RDD. So if you just collect it, map values on that, we should provide a function, of course. Okay, every x arrow x dot toString or just split by comma or something, and which gives another RDD. And let's see. So I just separated them by. So for this key, these are the values. So array of values, separated them by comma. All those values are coming here. Okay. So once you get the paid RDD, so doing all the transformations and actions is pretty simple. Pretty straightforward like any other RDDs. Okay. So generally, if you want to just to process the values part of it, we use that paid RDD.map values or flat map values, whatever you need. Okay. And yeah, so generally this is how we do like values.collect. So input.flat_map values. So I used map values. That's why I got arrays instead of actual. It's an array of elements. This is. So if I use flat map, they will become their independent elements. Okay. So you can even do that flat map values, comma separated values.map. I just counted each of them in that. So in just one line of. Okay. So that is LFS, HDFS, and reading files from directory and solving the small files problem very easily with just one method in Spark. So that's one thing. Next, if we have a comma separated file or any delimited file, and if we have a schema for that file, that means if we have a header for that file, if we can represent that with some schema, suppose if we have emp.txt, Hadoop fs-cat emp.txt. So you have, so this is just my 4 records, just tab separated. So if I want, I know these are like, if I know these are like employee records, and the first column is employee ID, employee name, and location. If I want to treat this as like a table, I need to map a schema for this. I will show you up to some extent in Spark Native, and we'll go further more into Spark SQL on the same topic. There you'll completely You can treat these as tables, and you can write your SQL queries directly on anything that you have semi-structured format, and you can easily convert that into your table. For now, how to make or how to map it with employee schema, we'll see that. So if we have case class, if we want to declare that as the same data in a table schema kind of stuff, so we can map that with, so case class, so ID, which is int, so name, which is a string, and location, which is another string, right? Okay, now, so I just have defined a case class. Now, I will read that file, okay? And let's see one by one. Well, RDD1 equal to, or EMP, well, EMP equal to sc dot text to file emp dot txt. Okay, so this is an RDD of string. So each line is treated as, this entire line is treated as one string, correct? Now, if you want to parse it, obviously you have to do parsed. What you can do, emp dot flat map. So for every record dot split by \t. For every record, you're doing record dot split by \t. So I'm not using flat map. If I use flat map, so I will get them as a separate strings. In the first, so instead of 3 records, so if I parse using flat map, I will get 4 into 3, 12 records I will get. If I use this, let me not capture this into any result. If I use this count, you can see 12. But if I use map, my element count will still be same, but I will get an arrays. Okay, so that's reason why I'm going to maintain only that arrays only. emp underscore parsed equal to map, so record dot split. Now, instead of taking the count of it, what I can do is, so after I split that, every element in the array, I will convert that into, so this is an array, right? So this is an RDD of array of string, correct? And if you just want to see one of the record inside it, it gets displayed you as an array. emp underscore parsed first, just check. So the first record is also an array of string which contains 3 strings. Now I want to give a schema to this. So val emp parsed underscore bean equal to some name I'm giving just, okay, emp parsed dot map for every record. For every record, what am I going to do? So employee I'm going to create an object of case class. To create my case class object, I need to pass 3 parameters: ID, name, and location. So how will I get my ID? So record is an array. So this record of 0, since in Scala we use this syntax, record of 0 dot toInt, also you can use, since you know the data type as integer. And similarly for other fields you can use, if it is string you can leave it as it is also, or if you want to trim the trailing spaces, leading and trailing spaces, you can leave it as string. Okay, now you will get the same RDD in terms of, instead of array, you have this time for every array you produce an employee object. So till now you were observing RDDs with basic data types or pair RDDs. So far, all the RDDs, RDD of string or RDD of integer or RDD of double or RDD of string comma string pairs. So till now we were seeing all the RDDs of basic data type. This is an RDD of objects, any other objects. Now with this object, if you have an object, you can group by their columns. You can identify their columns. For example, if you want to do this, so if you treat this as like an employee table, so just group by. So group by, and inside this object, in each object of this, so group by ID. So dot ID, underscore dot ID. Just ID is one of the column inside my case class. Okay. So on this dot ID, so by ID, I'm grouping it. And the result RDD is, so ID is of integer, so that is my key, and value part is the group of or a collection of employees, obviously, right? And similarly, if you want to filter by, let's say, filter this underscore dot ID equal to 1 to 3. It gives an RDD. Let's see what are the results of res 88 dot collect. See, I got only one record. So as good as like a column names filtering, I'm able to use them, and group by a column name, I'm able to do that. Similarly, you can do more operations that you can explore them during the Spark SQL, and we take this, the same example, to 1 or 2 more levels of extent. Okay. So here, like creating an RDD of a custom object or providing a schema, you can if I want to technically name this, whatever we did, creating RDDs of custom object type, if I want to make it functionally, applying a schema on a file's data or a semi-structured data, you are applying this schema. So first one is ID, second one is name, third one is location. And based on that column names, you're able to do some operations.
Okay, for unstructured data, anyway, we have to mention the schema in the file, so we can mention it, right?
Yep.
So in this way, everything structured and unstructured data will also become structured way.
Correct. You are applying a structure on unstructured data.
Okay.
Okay. So next, so that is with text files. Generally, this is a bit important topic. So go through this once again if you don't get it. So I just explained step by step, and there are not more than 2-3 steps. Okay. And now let me take how to read a sequence file and how to store a sequence file. Okay. Out of which, let me show you first storing it, and then let's read that the same sequence file which we store there. Okay. And in order to store a sequence file, we need our data to be in key value formats, because sequence file format is like, it expects a key value format. And let's say if I have a pair of tuples, like, so the string comma integer string, this is a 2-value tuple, 2-value tuple, 2-value tuple, and I have them a list. I can create an RDD with this, just a parallelize. Okay. Okay. So I can just parallelize this and make this an RDD. Same like your save as text file, we have save as sequence file. That's it. Nothing much difference. Data.save as sequence file, you can store it there. So data.sequence file. So /user /cloudera suq sequence out. Okay, so let me see. So the sequence out, let's find it out. Yeah, Hadoop fs-ls. See, you got your output file created. Okay, so this is just by looking at SUQ, you can identify that this is a sequence file, and where the keys format is text and values format is int writable. That's what we gave there. It automatically identified the data types also there very well. So string and int, they got converted into the sequence file, text and int writable, and it stored the records there. Now, if you want to read this back, generally what we have to give is same like text file, we have sequence file to read the sequence files. sc.sequence file, provide the path of this and provide the data type of your key and provide the data type or the class of your value, then it will be able to read it. Okay, so in simple terms, if I have to show you this ASC dot sequence file, let's say val seqrdd equal to sequence file, and give the path of your sequence file. So take the path of it and class of, just provide the class of your key, which is this, and class of your value. Then only it will be able to read the key and value classes clearly. So if I leave this as it is here, so it is now pay.dd of key as text and value as iterable. But these are your Hadoop data types, right? These are not your Java data types. Even if you want to see these contents, the serializer will fail to show you on the console just keys. So if you get keys, panda, k, snail, it should come, right? So, but this is an RDD of text, an RGS91. So if you try to collect it, since this is a Hadoop data type, you're trying to display as a strings there, collect expects the basic types. So it fails in serializer, conversion of serializer. The only thing is we only have to convert that into get. So sequence rdd.keys is another RDD which is of text type. So let me convert that, or let me complete the complete stuff. So map of every case of x comma y. So case every key value pair. So what I am going to do is x dot toString method is there, and y dot, so toInt, it's already iterable. To convert that, we don't have toInt method, but just get method is sufficient to make it. Okay, so this sequence RDD for every x comma y key value pair, I'm converting that into this way, x dot toString and y dot get, same stuff. Okay, and if we can collect these results, you will be able to understand this.
What in if we have employee ID as key and other as record, so I can still get x dot toInt?
Yes.
Okay.
Okay, so employee ID means you will have iterable, so just get the x dot get. No, you don't have toInt. That's what I was telling. You have to use get method on other data types on your text. This is like your Hadoop session. Okay, so conversion of your text format to string, we have two strings, and any iterable to int or long writable to long, double writable to double, just get is sufficient. Here also get is there. Here also.
Okay, okay. Thank you, Shiva.
Okay. Okay. Now, so this is how you can deal with your sequence files. Next, let me show you some other input formats which may not be your direct basic text input format. Sometimes if you produce output from your MapReduce jobs, they will be key value text output formats. Okay? The key and value will be separated by tab by default in your output files. So key and value, if you write a key and value will be separated by tab in your MapReduce output jobs. If you want to read them, we can read them by using key value text input format. And to read those any other Hadoop specific files, we have two APIs. One is the old API, and we have one new API as well. So the old API resembles similar to other two methods that we have seen. So till now we have seen, so text file, so sc dot text file we have seen, sc dot whole text files we have seen, and sc dot sequence file we have seen. Now we have sc dot Hadoop file. Okay, so if I explain a few of them, I can even leave up to you, so that it's all a matter of syntax, so that you will get only by practice. Okay, now coming to this. So if I want to read any of my MapReduce outputs which is in key value text format, so I want to read that, so I just have to provide what is my key and what is my value and read that. So first, suppose if I want to take any of my MapReduce outputs, you can see that. So Hadoop fs minus ls mr underscore outs. Generally, I use this at least to store my output sometimes. So let's say if you cat this, okay. So here, there's the keys and values. They both are separated by tab. Okay, this was just an output from one of my word count job or something, but it's a key value text format. So if you want to read such special text formats, so we have sc.hadoop file. But only thing is, if you want to use this, you have to import this, whatever the text format that you want to use, you have to import that particular class name. Otherwise, it will not able to recognize that type. So you have to use this import statements. Okay, and let's say same file, if I want to read it here. So it produces a key, another pair RDD, same like the one that we have seen in the sequence files, right? The sequence files it produced pair RDD of text and int writable. Here we have text comma text. As I specified, it is a text, and this is a text, and my file is MapReduce key value text input format, and the location of the file is this. If I want to, same process now, pair RDD of different types. If I want to get the keys, just get the keys and collect them, and only the keys that you want to collect. So input dot keys, you will get all the keys, and you should convert all of them into strings, right? X dot toString and collect this. Can see these are the strings that are present in, these are the words that are present in that file. And if you want to similarly process the values, same is sufficient. These are their corresponding counts. Okay, and the same way, any other file format that you can provide here. So even your ORC files or park files, all those things also can be read through this Hadoop file API. We'll anyway see that in the next slides. So one more flavor in this Hadoop file. So this Hadoop file API is like a backward compatibility. Even though you have the latest APIs also, will have the old API also working. So I don't think so it will go away that easily because it has extensive support for all the file formats. So the new API for this is the same. Instead of sc.hadoop file, we have new API Hadoop file. The naming convention is not so good. So very soon it might get renamed to something else. Okay. It may not have new API Hadoop file, something like that. So you keep on seeing, like once you enter into a Spark is like evolving like anything, and lots of methods get either deprecated or get renamed or get rephrased to something else. So you keep that transitions from version to version. Because I was keep observing from starting Spark 1.0. So now Spark 2.0. So lots of methods got deprecated and some of the concepts got changed to something else. Okay.
But how in real time it is if you don't have the stability?
It's
how
not about stability, Mamta. We already talked about this topic. I was telling you that Spark has lots of evolutions. And
no. I mean to say
changing the APIs. So at the same time, it will support a backward compatibility up to some extent. Thing is, in every, see, if you are using Tableau 8.0 version, and if they release new version 9.0, obviously there will be some improvements or some changes.
No, what my question is not that. When we,
it's not, I mean, it should not be about stability then.
No, see, what my question is, when you will be using one version, right? In the production, see, they are not going to change it very soon, right? So
I
they
got
will be.
your point, but it's not about stability. It's about upgrading your features.
So they need to upgrade if they want.
It's not the problem of stability. Stability means it's not functioning.
So only when they upgrade, they get new feature. Otherwise, it will work. Okay. Because I was thinking about the files which are in the production, and when there is something.
Those are like common for any tool, any software. Okay, right? Upgrading from one version to another version. How does it breaks for Spark? You think? Any tool will keep on releasing their new versions. And
but
introducing new features.
Very fast.
Of course, it has lots of user community, developer community. It keeps on changing very fast. Only thing is, it will provide you the backward compatibility. So always. So it will have up to, at least they keep on, see, if Microsoft is releasing Windows 10 or Windows 11, so they keep on telling that at least 2 to 3 releases prior. So from so and so date, we are not going to support this. Windows 7. After 2016, we will not support Windows 7. Obviously, you don't have an option. You have to upgrade. Correct?
Agree.
Yep. Same case. So they will also backward, they will also give you the backward compatibility up to some versions extent. They keep on giving the notifications that, so we are completely deprecating these features. Please migrate to this so-and-so version or not. That's why always say what is the prerequisite to maintain any application. What is the Spark version? What is the Scala version? In open source community, you should be so flexible enough, especially in terms of management of versions. By the time you complete your course, you might see 2.1 and 2.2 also. Okay. And you should not question that, oh, we got this. I mean, you should be in a position to adapt all the dynamic changes. So the next one, like, yeah, the same new API file. So just one example, if you want to read any such file, the same file with the new API, if you want to read it, so just give it as a text input format, class of, so either, so if key is long writable, in my emp.txt, and value part, yeah, this one you were asking, right? The same thing. What if I am reading my employee, so my key is, so
Yeah,
ID,
yeah.
key
Yeah.
is my ID, and value, I want to take the remaining two columns.
Yeah.
If I load the same thing with the new API, just API got changed, syntax got changed. I provided a emp.txt. It's a text input format. So I took the first column as a key and remaining everything as a text, and provided a conf object, and out of which I took the underscore dot, and on every underscore, I'm taking the second field of it. So if you just take this, and if you print this value, just a data.take of 5, I'm just taking only the values part of it. So I'm able to read this. So the first column is as a key, and entire text of the record as a text. So if I don't have a separate key, that's how it got treated as. And the second, the attribute. So inside this underscore 2, the second attribute, which is the content, I'm converted that into a toString. That's why you can see the contents of this as this way. To further have to process this thing. And more like, so if you see these APIs, you may feel a bit complex, but you will find a more easier way to process them, because here you are seeing as an array of strings, and again some delimiters in the strings, all those things. If you want to further apply some column level operations, you have to do few more steps to make it. That steps I have already explained there. But once we go into Spark SQL, once we build them into as data frames, as a tables, so you can run all your SQL queries or any of your Spark SQL operations on that. So mostly, hopefully, I'm planning that we may take that Spark SQL this weekend only. Okay. Now, so that way you can read your text input format files. So using the new API also. Similarly, if you want to read your ORC files also, the same way as we have seen for text files, so you can do that. So one of my ORC files, let's see. I think most of you guys know that how does a ORC files look like by now. I covered it for Hadoop sessions also. So this is one of the ORC file. that I have the same employee records. So if you just the contents of it, then you will be able to understand this. Okay. So this is my same employee record stored in ORC file format. If you want to read that, instead of the same API, so instead of text input format, we are giving this So instead of text input format, I just gave as ORC input format. And key for ORC, we won't be having any keys. So in that case, I gave it as null writable. And text is ORC construct. It has its own data type, ORC struct. It says a struct data type that it considers in the ORC. We don't need to worry too much internals of it. So just specify this in the ORC structure, so it will be able to read that. And once you able to read that, if you want to further process that, so same like for every pair dot underscore 2, just now we got that value part of it, right? From the key value pair, the same way. So for every employee details, so for every pair, so key comma value pair, I'm interested in only the pair dot underscore 2 means the second value. Obviously the value part, not the key part. I'm converting that into toString. If I convert this ORC struct into toString, I get a string of these values, but it may not be that simple. So if I want to process this, so if you check this, what I'm doing, the same string, I'm parsing it, that's it. So that is a string. For every string, I'm parsing this by comma and assigning that to my same employee object. So p of 0 dot toString of substring. So this I had to do a bit long because so split by comma, you'll get one string and then substring of it as ID, and then it's trim, all those things. Okay, I had to do a bit lengthy process here to make it as ID and to make it as readable here. But if you once we start learning Spark SQL, generally we try to read all these advanced file formats in the Spark SQL only. That gives you easy and fast syntax so that we don't need to make it so complex. The same stuff.
Real time we won't be knowing the it's not in a readable format, right? The ORC file. So in the real time we should be knowing the data type, right? Or the whomever is giving the file, they'll be giving the data type.
They should give the schema for that. What are the columns and what are the data types?
In which order it comes. So otherwise we won't be able to know, right? Because it's
otherwise we won't be able to know. At Math, what we can do is we can convert everything into string, because everything can be stored as a string and display them as strings.
Okay, or I can read few lines, I can see how it is. I assume that everything is same and then I can convert it, right?
Exactly. So, but the safe side, if you don't know the data types, convert everything into string. Not a problem.
Okay, so we have that option.
Yep.
Okay, thank you.
Okay. So let me not make it more complex by taking the Parquet and these JSON or other file formats examples. We'll discuss them during the Spark SQL only. Okay. Now, so with this, at least we saw different file formats, and so text files, whole text files, local and HDFS, sequence files, and key value text input formats, and regular text input formats, and ORC files we have. Now, let me take, this is bit of conceptual oriented. So here you can ask me questions because the previous section is more of like a syntax. Okay. You just can Google it out and find the syntax and start using that. So here, shared variables. Here again, like every time I keep comparing with MapReduce concepts, right? So here also, under this section, I will compare it with the distributed cache concept in MapReduce and counters concept in MapReduce. Okay? Now, so the shared variable means by name itself, the values or the variables will be shared across all the worker nodes of your Spark cluster. The concept of shared variables is similar to distributed cache in Hadoop. Once you share a variable, so that will get copied onto all the worker nodes. And shared variables will be accessible by all nodes, means they will get, each one of them will get a copy of it. Shared variables maintain a separate copy on each node. So in our typical flow, so my driver sends them. So driver will have a variables, and from your driver, if I call this any of the transformations that so far we have seen, so all these are nothing but making calls to your worker nodes, right? Anything inside that map function that you are doing on RDD, so this gets delegated to your worker nodes, any functionality that you are doing inside your map. So if they want some variable, okay, if they want some variable, let's say some I have some constant, some pi equal to 3.14, some value. So this is a constant, this needs to be available there. So if I pass it, if I don't put that into distributed cache of the worker node, what will happen is, if I'm referring here, let's say sum equal to 0, okay, and for every x arrow, so x greater than sum, always referring. This is a closure, right? So even though I'm not passing sum as a parameter to this map or here, but since this is within the scope of it, so this value can be copied to all the map tasks. Let's say if I have this map task spanning, if I have this partition on this RDD is, suppose, assume it got split into 100 partitions. Now what will happen is 100 tasks will get triggered. This is clear, right? So far you have been seeing this. So how many our partitions are there? Those many tasks we were observing. And the ideally Spark is configured such a way that so it will get small task sizes. Generally small task sizes so that they will get quickly finished off, not so huge tasks which take a 1 minute or so execution. So it will span tasks not more than 5 seconds, 10 seconds, around that. Okay, so we don't have concrete figures for that, a rough numbers. Like it tries to configure your task sizes small as possible. Okay, but not too small that you think that it may cause an extra overheadache in maintaining, in launching those tasks and killing those tasks. Not that small as, okay? So in this case, if this RDD if it is having 100 partitions, if it is submitting 100 tasks, out of which let's say I have only 10 worker nodes. Okay, so this partition, this RDD might be of 100 partitions, but my cluster may not be 100 node cluster, right? Obviously, I just have a 10 node cluster. So that means 10 worker nodes. 10 worker nodes. That means 10 executors. So in each worker node, one executor JVM will be running. And inside the JVM, multiple tasks can be running. The same task again and again, or one after the other, your tasks may run in parallel. Generally, one after the other, your task may run in sequence if you don't have those many number of executors or those many tasks if you can't span it. Generally, the same JVM can be reused also for multiple tasks based on the configuration. So let's not worry about those admin stuff. Okay. Now, assuming this scenario, so if this is the case, if you have 10 executors and 100 tasks, so that means on an average, if you take one executor will run 10 tasks. But if you are using a regular variable instead of a shared variable inside any of your map function or transformation or action. So your transformations closures or actions closures, whatever it is, if you use a regular variable for every task, a separate copy of the variable instance will be sent to the worker node. That means if you have this sum as a variable, if you use it as a regular variable, then this will be sent 100 times to 100 tasks. 100 times to 100 tasks, this variable will be sent, communicated, transferred. Whereas if you make it as a shared variable, so this variable will get shared only once per the node. Only once per the node, and it will be stored in the worker node in the RAM memory until your Spark application completes your execution. Until your Spark application finishes off. So that means you're not sending the sum variable again and again there. Okay, seems like you are on video, Mamta, and feeling sleepy. So I'm turning off your video. Okay, thank you. So I hope you got the problem statement. If I use it as a regular variable, for every task, this variable's value will get transferred to the task. In this scenario, it will get transferred 100 times. But if you make it as a shared variable, how? We'll discuss. Okay, let's park that aside. If we make it as a shared variable, instead of a task level, per machine, at the beginning of the application, whenever you make it as a shared variable, that time it will get copied onto all the worker nodes only once. But one restriction on this shared variables is that they should be constants. Shared variables are immutable, and any changes to those shared variables that you make in the worker nodes, any updates to those shared variables will not be propagated to the driver. I mean, I should not say driver. Any updates that happen to the shared variables will not be propagated to other worker nodes. So if this worker node makes this sum as 10, so first worker node, your second worker node may treat that sum as 0 only, because that's what you have initially sent to that worker node. Your shared variables updates will not be propagated to other worker nodes. It might be a bit difficult, or it might look a bit strange for you, but so this solves some of the use cases what it was intended for. Okay, so you don't worry about what is the use of it if it doesn't propagate to other worker nodes. Yes, you will find a use case. Okay, we'll see that. Now, coming to this shared variables, we have two types. One is a broadcast variables, and second one is accumulators. So broadcast variables are exactly same as your distributed caching. Distributed caching mechanism. Okay, and accumulators here. So the point that I told you, updates will not be propagated to other worker nodes. So that holds good, but still we achieve the counters concept here. So these are for counters. How we achieve, we'll definitely see. Here one statement I am making is shared variables are immutable. Immutable and should not be so large, because these are being stored in memory, should not be very large. Of course, the same limitation as our distributed cache there. Okay, and they should be able to fit in memory. Shared variables will not support any update operation on each node. So make a note of this line. So updates will not be propagated, because this line may seem contradictory for you when I talk about accumulator. That's why I want you to concentrate on this statement and how I will clear that confusion at the time of accumulators. Updates will not be propagated to other nodes. Okay. Now you have, out of the two types, so you have broadcast variables. And first of all, why do you need a shared variables? This is the story behind this. Spark automatically sends all variables referenced in our closure to the worker nodes. While this is convenient, it can also be inefficient because the default task launching mechanism is optimized for small task sizes, and you might in fact use the same variable in multiple parallel operations, but Spark will send it separately for each operation. The same thing that I took with this example. Like, so when you have an RDD with 100 partitions, you will get 100 tasks. You will run those 100 tasks on 10 executors. Obviously, 10 tasks will be running on each executor. And the same variable, if you copy it once, the same variable can be useful for all the 10 tasks that are running on the same, because it's a constant.
When it is a constant, we can save it as a value, right? We can send it as a value to function.
Correct. That's what we are sending. So you are sending, like, you are sending a plain value instead of variable.
Or I can send it as a variable to that, right?
If it is a collection.
One more variable.
See, that's what I'm telling. If you send it as a regular variable, every task will have a separate instance of getting copied there.
Okay, so this
okay.
is.
So you will get 100 times that value getting copied. If you make it as a regular variable, for 100 tasks, 100 times the value will get transferred. But if you make it shared variable, only 10 times for the 10 executors or the 10 workers. Okay?
Okay. Across the number of nodes, whatever we have, that many times.
Correct. Exactly. Now, next, you'll see that's the advantage of. So the broadcast variables, you can only send once for a node. So broadcast variables allow the programmer to keep a read-only variable cached on each machine rather than shipping a copy of it with each task. I hope this line is clear now. And Spark also attempts to distribute broadcast variables using efficient broadcast algorithms to reduce communication cost. And how they is like, so the variables will be sent to each node only once and should be treated as read-only, and updates will not be propagated to other nodes. And in such cases, you won't be able to change the value of the broadcast variable except within the driver code. So if you make a variable as a broadcast variable, all workers, meaning inside your map, inside your transformations, inside your actions, you can't change that. Inside a map, if you have a closure, this is what gets executed on the worker nodes. But actual logic that you have will get executed in the driver. So in driver, you can change them, but not on your slaves, on your workers. And if I have to, yeah, by
through the driver program or the main program, we provide this value.
Correct. Yep. Okay. And some of the properties of them are like broadcast variables are immutable. They should be fit in memory, distributed to the cluster. And these same are like its limitations. Have to be fit in memory on one machine. That means that they definitely should not be anything super large. Secondly, broadcast variables are immutable, meaning that they cannot be changed later on. This may seem inconvenient or strange, but it truly suits their use cases. Let's see how to make a variable as broadcast variable. Just use that variable name in sc.broadcast function or method. So we have on Spark context broadcast method. So if I pass anything, an object, a string, an array, or anything, a list, anything you can broadcast, a map, you can broadcast anything. Only thing is that should be small enough to fit into your RAM memory. And in your real-time clusters, you may go up to hundreds of MBs, but may not be more than a GB or so. You can go up to hundreds, maybe couple of hundreds, or up to max 500 MB or so. Because that much of memory you are occupying on each of the worker nodes RAM. Okay, so if I want to simply make an array as like val br broadcast variable, so sc dot broadcast of, I'm just sending as an array of just some numbers 1, 2, 3. So this got broadcasted. Now, whenever if you want to refer that value in worker nodes, you can get it like broadcast var dot value. So you will get this value in your driver also the same. Dot value is to get the value of broadcast variable. Now, if you remember the ones that we did using the distributed caching mechanism, map side joins, right? In MapReduce concepts using the distributed cache. So the map side join, how we achieved. Let's see that simple use case using the broadcast variables. Let's say I have two data sets, simple data sets with two columns only. With two columns, I have one with the name, employee name and ID, and the second table or the second file with employee ID or this way, like so, name and course ID or whatever it is, and ID / the course. Okay, so if I have this way, so if I want to join them using the distributed cache mechanism, so one will be loaded into distributed cache and that will be used to map with the other table when you are processing record by record, right? The same we do here. So if you just check here, so here I'm just reading it from a collection sequence. So now this is EMPS. Employees RDD is nothing but a employee names and their ID. And in the courses or the tools that they know, the tools RDD that they know is nothing but we are storing that on the. So this is the ID of the employee and which tool he is famous at. So let's say Siva is tied with big data and 101, we don't have anyone, is expert on C#. And Ramesh is tied to 102, which is Scala, and Ravi is tied to Java, and Rakesh is in Oracle. Okay, if I join these two tables now by ID, so this table with second column and this table with first column. Simple one I'm taking. So before doing that, so I broadcasted one of the table because this is simple enough. So I can store this tools RTD, converting that as a map so that I can look up by key. And that map I'm broadcasting it. sc.broadcast of tools RDD collect as map. And the map is integer comma string. Here keys is integers and strings are values. Now I will process this record emps.rdd. For now, let's not worry. Let's take this as just like a map function only. Okay, but map partitions we'll see more. I use that for a better optimization here. Okay, but without that also we can do this, or let me try to do this without it. emps rdd dot emps with tools dot map of for every row. Okay, so for every row dot underscore 1, comma underscore 2, So I'm producing this input EMPSRDD. I'm taking that as it is as 1 and row dot underscore 2, the ID as it is, and I'm bringing its corresponding course from this collection map, this one, broadcast tools dot. So what I will do is broadcast tools dot value. So I will get the value of it. Broadcast tools dot value. I will get a map now. So on map, I have a method get by key. Okay. So get by key. If key is not there, so what should be my default value? For that also, we have get or else method. So you will see this method available many places. This way, if you find a value for that key, you will get that value. Otherwise, you will get the default. Okay. So get or else. Get or else. So what should I pass as a key here? Row dot underscore 2. That is my ID for this. And otherwise, -1 as the default value. Okay. So now int of any, if I print this now, employees with tools, just take them, so you can find them joined there. Siva with big data, Ramesh with Scala, and Ravi with Java, and Rakesh with 104. You got it. Right? This way, you can broadcast, because this variable, whatever you are using, this broadcast map, this needs to be available in each of your map tasks, each of your tasks. Otherwise, you can't get this. In every node, this copy should be there. Otherwise, you will not be able to find what is its value for a given ID. Especially, so these will be helpful in cases of joins a lot. Now, so if this table is big, if it is having 100 partitions, 100 times this, you have to pass it as a collection, and you collect there, and you process that. So instead of that, if you have 10 worker nodes, only 10 times this map will be broadcasted. Okay, so that's the advantage of your broadcasted variables.
We can send any object, right?
Anything that can be fit into that. That's it. Okay.
So are we going to really use it in the real-time scenarios?
Of course, that's just why I gave you, right? Map site join, the same thing if you want to do in a MapReduce, you have to use distributed cache and need to write a lot of program there. The same distributed cache join, map site join, I achieved in 3 or 4 lines of code, right? Right? Okay, so as of now, I didn't discuss about map partitions. That's why I achieved the same functionality with map only. Okay, so you can have both the solutions here for it. Okay, so next, let me take up the accumulators. Okay. So accumulators, on the other hand, they are also shared. They are also part of your shared variables, and these are not just for read-only purpose, and they are equivalent for MapReduce counters. They can be used to implement MapReduce counters or sums. When we normally pass functions to Spark, such as a map function or a condition for filter, they can use variables defined outside them in the driver program. Same line I have written. But each task running on the cluster gets a new copy of each variable. Here, one more thing. In the previous slide, when I was telling you broadcast variables, I told you that so when a map function or a filter or anything that you are using and that use the variables defined outside in the driver program, they will get a separate copy of each of these variables. Now I'm telling a separate new copy of each variable. Every time they get, all the tasks will get 0 if I have a sum as 0. And updates from these copies are not propagated back to the driver. So there is no way that you can achieve the counters concept without the accumulators. In one single line, I have to conclude that. The code below shows an accumulator being used to add up the elements of an array. And if you want to make a variable, if you want to declare a counter, so you declare this using the sc.accumulator and specify your val accum. So you can give the name to it, my accumulator, a description to it, and with the initial value as 0. Now this accum is the accumulator. Okay. So let's see a simple array sum. So I can declare that as accumulator. I declared one accumulator. This is like a declaration of an accumulator. Okay. Now an accumulator is created. When I'm processing my array of elements, so this will become an RDD of integers. So for each, I'm getting the sum this way also, like. Right? This is an RDD, one of my, well, just pair RDD. This is a regular RDD of integer, right? So pair RDD dot collect, it's 1, 2, 3, 4, right? And pair RDD, parallel RDD, that means. Okay. So for each, I'm trying to sum into my accumulator. For each x, accum plus equal to x. So I'm not doing any other processing, any transformations here. I'm just summing up into my accumulator. Now, if I use accum.value, I can see 10. So you may get a doubt. Can't I do with this a regular variable? Yes, you may get it. Now, I have a solution for that. I have a proof for that. So let me take two variables. One is a accumulator variable and another one is a regular variable. Okay, and let me take process. Generally, why we use accumulators or the counters concept in MapReduce or Spark keys, just to count how many bad records are there, how many good records are there. Any scenarios where you need counters. The same typical scenarios that you need counters in MapReduce. Now, so val in RDD, input RDD, so sc dot text file of readme.md, just a file I'm reading. Okay. Now, let me declare one regular variable and one accumulator. Okay. So one val blank lines. Okay. So blank lines sc dot accumulator of 0. Okay. So I declared blank lines as an accumulator and val count equal to, or you can make it as var because you want to increment it, right? Not a var. Val means constant. Var means this thing you feel like. It's a regular variable. So this is one counter and this is another counter. So what I'm going to do is now, I'm going to read this file every time. So in RDD dot map of for every x or for every line arrow. So if my line is empty, then I will increment the counters, both the counters. I will increment blank lines and I will increment the count also. So file dot for each, for every line, or either use map or for each, either of them is fine. So if line dot trim, if you're not producing anything output, better to use for each, because map expects the same number of elements from the output. So what I can do is, for each of this, for every line arrow, so if line dot trim dot length, after removing the spaces, if the length of it is less than 1, then do this. Do all this stuff. If line dot trim dot length less than 1, then what am I doing? So blank lines plus equal to 1 and count plus equal to 1. This is what all I am doing. So blank lines plus equal to 1, I am incrementing blank lines by 1, count plus equal to 1. Okay, so I am closing these two curly braces and my for each method. So this is very clear, right? If the length is less than 1, that means it's a blank line. I'm incrementing both count and blank lines. Now, you should have blank lines and count values to be incremented, right? So blank lines dot value, see how much? 35 is there. And how much is count? It's still 0. When it comes back to the driver, see here, anything that is present in this will get executed as tasks, but anything inside here is within the driver. So your updates are not propagated back to the driver from your tasks. If you do the same thing once again, the blank lines was already 35. Now this time it becomes 70. See this? Run the same example once again, process this once again, and see blank lines dot value. It got 70. It continued from there. So it's I didn't specify this. I should take it from 0 again, right? So already it was there in all the worker nodes. Of course, there is a small bit minor point that you have to catch. I will explain you later. But that value onwards, it continued again. It's a counter, keeps on getting incremented. How many ever times as you process this file, those many blank lines will keep on incremented. So here this count, as always, remains the same 0. It's again 0 when it comes back to here. But do you think that it's not getting incremented? If you think like that, you can use your println statements here. So if you want to check that, so why don't you keep a println statement? So println of blank lines plus blank lines count. If you really feel like that is not getting incremented, you can see both of them are getting incremented equally, parallelly. So if it is 30, if it is 30 within the task, because the println is also within the task inside the map and which is getting executed by your worker. Yes, they both are getting incremented. When you come out of that and when you come back to the driver, your count is 0. It's not propagated. Okay, so that's the reason you need accumulators if you want to propagate your counters back to your driver.
This is also available in all across nodes, right?
This is also available
across nodes, but
blank lines equal to 35.
No, accumulator.
Wow, that's what accumulator here in this.
Yeah,
area.
so
yep.
When everyone are writing it, there will not be any overrides or same time multiple.
Coming there. I'm coming there. Okay. Think how, if you will really get surprised how it got implemented in the backend. Okay. So let me come to that. If I have any points which I have to cover before that, I will try to cover. Of course, it is possible to aggregate values from an entire RDD back to the driver program using functions like reduce. But sometimes we need a simple way to aggregate values that in the process of transforming an RDD are generated at different scale or granularity. So just these kind of things, we need them. Okay. So next, so you will see, I will explain that how these got implemented in the backend, and you may not digest that easily. Note that tasks on worker nodes cannot access accumulators value. So they may not get the latest accumulators value just using the dot value. So what is the copy? Here I have only one task. That's why it's keep on getting increased. And that's why you may see that that parallelly getting increased there. Only one task might be there. Cannot read accumulator value in task. Okay, don't come to any conclusion now. Let me. So here, whatever your next immediate question is. So if you didn't understand properly, the next immediate question is, so how can the println statement printed as a log text line without the value? So this is I'm keeping you on mute, Ananta. getting noise. So this is a local variable. I mean, this is as good as a local variable getting incremented for this task. Since we had only one task for this job, so you can see all the 1 to 35 getting incremented. But when I try to access the actual blank lines from the driver value to this, I'm not able to. Blank lines dot value. If I try to, if I have multiple tasks, okay, if I have 10 tasks, so one task is incrementing the blank lines to 10, and the second task has found blank lines, 20 blank lines. It has 20, and third task found 30 blank lines. It has 30. Now overall count is 10 plus 20 plus 30, which is 60. That 60 value you will never get in any one of the tasks. That means that whatever the statement that I made initially, your updates will not be propagated to other nodes, which still holds good. On shared variables, I made a statement that updates will not be propagated to other nodes. Then how the driver is getting the total counter? Obviously, your accumulator will get a initial copy of your worker nodes will get a initial value of the accumulator once when application is started, and when a variable is made as accumulator, whatever the initial value, that value will be sent to each of the worker nodes. First, suppose if I have this driver, and here blank lines is 0 initially, and I distributed. I made it as accumulator. Now I have 3 worker nodes or executor. Executor 1, executor 2, and executor 3. Now, what is happening is it received blank lines as 0. It received blank lines as 0, and it received blank lines as 0. Now, so this executor is running a portion of the data. Okay, so one block, let's assume one block, and it found 10 blank lines. It got incremented by 10, and it got incremented by 20, and it got incremented by 30. But no executor has the actual final result. Obviously, once this task is finished, before it gets finished, this value will be propagated to this updates number of times. They don't have a value to update also. This is a local variable that gets incremented here. This final value will be sent to your blank lines. So it will simply receive it like the same plus 10, and same plus 20, and same plus 30. If you are doing any other operations, like if it may becomes minus 20, since in counters it may not be having so negative values, but in doing any other operations, like say if it becomes minus 20, we'll get finally 20. But if it is 20 plus 20, you will get your 60 value in the driver. Okay, so that's what the first statement says. Note that tasks on worker nodes cannot access the accumulator's value from the point of view of these tasks. Accumulators are write-only variables or write-only variables. This allows accumulators to be implemented efficiently without having to communicate every update to other nodes. We create them in the driver by calling this. Maybe if I want to show you those printlns also, I will put this println statement. Okay. 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 So if I don't use blank lines dot value, it will work. If I use this, so get error. Error cannot read accumulator value in task. Sorry. If it is just a blank lines, then it can. Okay. Then, so we create them using the accumulator that we know already, initial value, which returns on accumulator. Worker code in Spark Closure can add to the accumulator with its plus equal to method. The driver program can call the value property on the accumulator to access its value. Whenever it calls the dot value, that time it aggregates or gets the final value. The value of our accumulators is available only in the driver program, not in any of the worker nodes. Okay? And one problem that one more point that we should keep in mind is that the speculative execution that you have seen in MapReduce, which means, so one of the map task is running slow, or one of the map task is failed. So the same copy of map task will get triggered on another node, right? So what if you have a counter inside that map task? So it may get incremented twice, right? Same problem. We have it in here. But here also we have that speculative execution. If a task fails or if a task is running slow, it may launch another copy of the same task on another worker node. But in order to have your counters duplicated or incremented incorrectly in case of such speculative task scenarios, so Spark community recommends us that use these accumulators mainly if you are using it for counters purposes. So use them in actions instead of transformations. If you use in transformations, it may not be guaranteed that you may get the exactly correct value if there are any task failures. If there are no task failures, obviously you'll get the correct value. If there is a task fail and the task got relaunched again and again, then there is no guarantee that you may get exactly correct value. But if you use an action, then definitely it maintains that internally, it maintains somehow and you will get the proper value there. Okay. So accumulators used in actions. Spark applies each task's update to each accumulator only once. Thus, if we want a reliable absolute value counter, regardless of failures or multiple evaluations, we must put it inside an action like for each. That's why the better way than using inside a map, we used it in for each, which is an action. For each is an action, right? Map is a transformation. For accumulators used in RDD transformations instead of actions, this guarantee does not exist. An accumulator update within a transformation can occur more than once in case of speculative scenarios.
Then here also my result will be wrong, right?
Why wrong?
Because when I say sum, a speculation happens, it will run another task.
That's what I mean. I was telling you, right? Don't worry about the internals. But Spark guarantees that if you use inside an action, Spark will guarantee you that it will get updated only once. How? You don't worry about it. Okay?
Thank you.
Yeah.
Are we continuing?
Yes, just a small topic. So map partitions. So so till now you have seen map and flat map. And whenever we are getting that map partitions, I was telling that I will explain you sometime later, right? So let's see that now. Yeah, so it's a small topic. Let me complete. Okay. Yep. Sorry. So map partitions, the concept is very simple. Per partition, run one map. And inside that you can invoke one another map function for each record if you want. Generally, your map is for apply your logic on each element separately, right? Let's say, so in simple terms, the usage of it you will better understand. Let's say I have a 1 million records, like, or a 10,000, 1 lakh, 10 lakh records or elements. I say elements. So inside this 1 million elements, if you apply .map, any function, any closure that you write, x arrow, x or something, so this closure that you write will get executed 1 lakh times. But in case, if there are, let me take you one example. If there are any DB operation where you are going to insert this, each element, one element into your table or your RDBMS or something. So inside your task, every time you have to open a connection for every record, like it's a fresh element, like it's every time. So for every element, you should start with X arrow. That means for every element, do whatever you want to do. So here you have to specify for each element, open a connection connection statement to your RDBMS or any DBMS, okay? Connection to DB, and then so once you make a connection, then let's assume X dot put into your DB. So this means if you have 1 million records, if you have 1 million put statements, you are doing connections 1 million times. This should be ideally a one-time statement. But if you use inside a map, there is no way that you have to start with X arrow. Because every element, you will process it separately in map. Now, instead of doing this, so if I have such a facility that this 1 million records got distributed only into 10 partitions. So I got this 1 million records distributed into 10 partitions. What I can do is dot map partitions or partitions. So here I will get a partition. I will process a partition by partition. For every partition is nothing but another collection, right? So here, so if I have 10 lakhs, 10 partitions means 1 lakh elements in one partition. Exactly. So that means it's a small RDD. You can take your partition, you can consider your partition as a small RDD inside that, or a child RDD. So for this partition, you open a connection. And so 1 lakh records, for 1 lakh records, you are making a one connection. Now, since this is another RDD, you apply your map method. You process them separately here. Partition dot process each element separately now once again. Generally, the purpose of map partition is that if you have any initialization stuff or anything that you don't want at each element level, but having done once, so you do some initialization work only once and then make use of that initialization value for all the elements, then we have to go by this way. So do some initialization for every partition, do your initialization stuff here, your regular statements, plain statement, and once all completes your initialization stuff, so making use of this, you call your partitions.map, so which gets applied on this, whatever the map function that you want to try to do here, so put that inside this. And typically you will see in any map partition an initialization, and again after that a map function definitely being called from inside that. So with this way, you will be making to your DB only 10 connections, which is an efficient way of doing it. Right? Now, let's see the same with an example. So map partitions can be used as an alternative to map and for each, because map will apply on every element and for each also apply on every element. Map partitions is called only once for each partition, unlike map and for each, which is called for each element in the map. Inside that partition, you can process each element separately again using map. Okay? The main advantage being that we can do initialization on per partition basis instead of per element basis. Consider the case of initializing a DB, the same stuff. Get iterator as an argument for a map partition. through which we can iterate through all the nodes. Okay, same thing, same stuff, blah, blah, blah. In this per partition, we have three types of per partition methods: map partitions and map partitions with index of the partition number. In which partition you are processing right now, also you will get with map partitions with index. And for each partition, same like your map partitions only. But here, for every partition, you will get another partition. Iterator means a collection of elements. Obviously, partition is nothing but, RDD is nothing but a collection of elements. And partition is obviously another collection. The same thing you can process. One good thing is you by default you will get iterator on this. So if you just see one example, you'll better understand this. Like, let's say I have taken the with index one only. If you understand with index, if you want to just use map partitions, just drop using the use of index. That's it. So that's why I cover with index, so that it covers both. Okay. Here, let's assume. So if I have this collection, so without partitions, it may have only one in this case, because if it is small, but I'm making it as a 3 partitions. How can I specify partitions? I hope you guys still remember the extra second parameter you can give the partition number. So I have 3 partitions in this now. So whatever I do now, so let me explain you the code first. So here, map partitions with index. Index represents the partition number. Okay, we already know. Iterator to iterate through all the elements in that partition. Okay. Now, for every index comma iterator, so what I am trying to do is, I got called in so and so partition. I'm printing that index number and take that iterator, convert that into toList. In a normal use case, we'll do the initialization before iterating through each element, generally here. But here, I'm not making into any RDBMSs here. So simple list. So iterator.toList, you got a collection, and on that collection again you are applying map. For every X, use X arrow index.iterator. Because finally the map partitions also expects the another iterator as. Okay. Now if I collect this, if I execute this, then only it will get executed. So it got called in partition 0, called in partition 1, called in partition 2. So it got 3 partitions. So this got called once for the partition. Only once per the partition. And so how does your elements got distributed? For your partition 0, there is only one element, yellow. This yellow got processed in partition 0. And red and blue got processed in partition 1. And the cyan, black got processed in partition 2. So any initialization stuff, if you want to do it at a partition level, you can do that. Generally,
this is more like indexing in database, right? So we need not to
no, this
entire
is not
file.
that index. It is not that index. So that index is indexing, improving your search performance. This index tells you in which partition the current.
I got it. I got it. Suppose if you have 10,000 rows,
Yep.
let's say that you have states, like each state will go to different partition or a bucket.
Correct.
So I will look for one partition, not the entire file, right? So
Again, this partition is not same as your hive partition. This partitions we were talking about from the beginning, right? Spark partitions, which is equivalent to a block in HDFS.
yeah.
Right? This is not hive partitions or hive bucketing. Getting my point?
So even though that this partition cannot apply here in the for the files, so that I can take very less time.
See, this is the same. Like partitioning, whenever you load a RDD, that gets split into partitions, right?
Yeah,
So
whatever it is for the parallel processing.
For parallel work, that's what. So if you have any initialization stuff, if I have this RDD2, so without any partitions here, let's say if I have, since this is small data, you may get only one partition there. Now, if I use the same on RDD2, so it may have only one partition. So all the elements got distributed. So you may be, so based on the, okay, so mapped dot collect. So all of them got processed in one partition.
Where exactly we use this concept then? So if it is through the like HDFS partition.
See, yeah, where exactly we use in the sense, whenever we need a initialization at partition level, example real-time case is that if you are making any connections to RDVMSS, or if you want to have anything that get initialized only once instead of all the elements, that you can do that there.
Okay.
Okay. And you can use any one of them. So mostly if you need index number also in which partition exactly it's processing, you can use with index. Otherwise you can use map partition. For example, in the previous example that we have seen here, the joins here. So here, if I use, here I'm not doing much initialization here, of course. So that's why I might not need map partitions also. But always the better scenario is like, so some places I have read like map partitions are more efficient than using your map, because inside map partition you do your map only. So here if you observe this now, emps rdd.map partitions, how many partitions are there for each partition? So again, partition.map, and inside each partition you will have a separate element. For every element you are doing x._1 and x._2 and dot casted tools. Right? So before starting this operation, if you have any initialization stuff, you can do that. That's the plan. That's the idea behind providing that. Okay. And even if you have a plain map, even then you can use them. Similarly, the same map you can put it inside a map partitions. So for every partition, another map will get called to process each element, each of its elements. Okay, so that's a bit about map partitions. And if you have a RDD with numeric, meaning int, double, float, all those things, you can apply these numerical methods. Count, dot count, dot mean, dot sum, RDD dot sum, RDD dot max, RDD dot min, all these things. Okay, so that's it. I will stop it here today, and tomorrow we'll discuss the runtime architecture, the cluster level. So we'll go a bit deeper into the drivers, executors, cluster manager, same as your application master. Okay, or all these things on cluster.
Will you please place this file in the shared location so that I can go through it again tomorrow?
I mean, why are you asking so pleasingly? Because every time I'm keeping it, right? You're asking,
no, if you
I'm
keep
not
it,
keeping any time.
no, if you keep it now, I'll put it because I can't access the drive thing. I can't read it when I'm going in the ghost train or something. If I do it, I can immediately keep it and I can read it
Okay.
while going in the
I
market.
don't directly keep these slides as it is. I have to convert them into PDF and then I will upload it. That's the problem.
Okay. So because morning I'll not have time. That's my concern.
Okay.
Until next day evening. By that time I can't do anything.
Okay. Yeah, I will put that entire the Spark one second as a Spark part. Okay.
Oh, okay. So that I can put it in another thing and I can read while going in the morning.
Okay. Okay. No problem.
Thanks, Shiva.
Okay. Thank you. So any questions?
Shiva, on that joining thing, like, hello? Yeah, you explained in one of the slide that join example.
Correct.
Yeah, so where exactly we are specifying that we are joining on the particular field, like ID in our case?
Exactly. You can see here. Okay, it's a bit of like abstract kind of. It's not a straight join I'm doing here. So for every x dot underscore 2, x dot underscore 2, this is the one that you are using. And the same value you are passing and getting its corresponding value from the map. That means its mapped value, its correct matching value, you are getting it here. So you are doing it by ID then. So x dot underscore 02, x dot underscore 2 is the column that you are joining between these two.
Okay, okay. Yeah, got it.
Okay. Yeah, you can give me a call in another 5 minutes, Mohit. Okay.
Okay, Shiva.
Okay. Thank you. Thank you, guys. Thank you very much for your support.